Thank you, Susan. All right, well, thank you. Today's webinar, Burner Retrofitting Real-Life Stories, was actually initiated by audience demand. Especially after viewing our webinar last May, which was entitled Burner Retrofitting, the What, Why, and How, which gave those contemplating a burner retrofit a clear understanding of the considerations that one should take to assure not only the proper selection of the burner for the job, but what also needs to be considered for a good installation and then positive running results after the install is completed. So in essence, our customers wanted more than just to be educated on the what, the why, and the how. They were saying, okay, well, that's all real, that's well and good, but how about some real life stories which employed these concepts, and including the hurdles that had to be overcome, and then what was the outcome? So with that request and idea in mind, this is what our program will consist of today. First, I thought it wise at least to briefly review the key points we covered last May, including the drivers for retrofitting, and then we'll briefly review the key considerations for a successful job to occur. Then after that, we'll go into the two inside stories, including a major hospital here in Milwaukee, which would be a large institutional type job, very close to an industrial job, and then a senior living center in California, which would represent a commercial heating project. Now, as far as the major drivers for retrofit are concerned, they'll all easily fall into these major categories: reliability, economics, and environment. Now, reliability is often impacted by the things shown on the screen now, especially when considering that the average burner has a life of about 15 years. Now, there are some exceptions out there. You've got robust designs that will give you more than 15 years, but on balance, that's about what we're getting. And then there's the problem of obsolete burners and the inability to secure parts and service. This is a major concern. Or maybe the process or the heating load has been increased, or maybe it's been reduced, and the burner can't keep up and is cycling incessantly, which is very, very inefficient. And then we have the economic considerations, and these are impacting those operational expenses which I've got earmarked with the red arrows: fuel, repairs, services, and then supplies that would tie into these services and repairs. Now, one of the big culprits here is oversized burners causing excessive cycling, easily causing fuel expenses to escalate by 15% or more, depending upon the extent. And here are the reasons. Firstly, when the burner is oversized to load, it hangs at low fire most of the time, and the excess air is extreme, and this needlessly wastes fuel. And let me show you why. Normally, we try to keep burners operating as close to 3% O2 as we can, which means many burners need to be operating most of the time at 50% of their rate or higher. Now notice on the screen now, for every 2% increase in O2 over the benchmark, which would be 3% O2, we lose 1% in efficiency. And that's why proper load sizing is so important. Now, the other problem with burners oversized to load is many have low turndown ratios, low turndown capabilities. And this is what drives the cycling costs, because the burners are cycling off and on several times per hour, triggering the pre- and post-purge losses, driving up fuel costs, which I said can be 15% or higher over the benchmark. The other thing that can drive fuel costs is the combustion control system, using linkages and cams, causing deflection, wear, hysteresis, and slip, and this then throws off the fuel-air ratio, versus using motorized actuators with a central control for balancing and controlling the fuel and air ratios. Now, this provides consistency and repeatability throughout the modulating range, hour after hour, week after week, month after month, and year after year. Then we also have those atmospheric changes, which can offset combustion causing us to go fuel rich, which can be very dangerous, and I'll show you this situation a little bit later with a case study. Or it can go fuel lean, too much excess air, very inefficient. Now the O2 trim system can compensate for this, especially if the swings in ambient temperature in the boiler room are excessive. And lastly, we have the environmental driver, with a big culprit being NOx, or nitrogen oxide emissions, which is a precursor to ground level smog formation. And to attack that problem, the industry has developed low NOx burners. And some of these will include FGR, flue gas recirculation, to further lower the NOx even more. Let's say from 30% with the low NOx burner by itself down to 9 parts per million, and as low as 4 or 5 parts if we include selective catalytic reduction as well. All right, so much for the brief market driver review. Now let's move on to the key retrofit considerations, beginning with the application information, including the boiler make, the boiler model, and the furnace dimensions and pressure to which the new burner would be affixed. As far as the make and model of the boiler is concerned, this is very important to the manufacturer supplying the burner, as it often impacts the burner model and then the type of the burner that he will apply. Then there's the all-important furnace dimensions and existing furnace pressure that the burner will be firing into and against. These elements can make or break a job. Also, we want to note the operating steam pressure or water temperatures, and if the boiler is able to match the load and at what firing rate. You know, is it cycling or struggling to keep up? Also note the boiler rating on the nameplate, and make sure you know it's the boiler's input, not output, as the input is what the burner needs to deliver. Now, it seems intuitive, but often incorrectly noted, and this causes problems. Next, we have the required clearances. Again, something which needs to be paid very, very close attention to. For instance, besides any encumbrances in the boiler room itself, what are the required clearances for the new burner? Things such as depicted on the screen with the red arrows. The location and clearance for the control panel. Does the blast tube need to be extended in order for the burner to clear any obstructions on the boiler's front, such as is shown here in the picture with the smoke box on this firebox boiler? And finally, what is the distance from the burner's blast tube to the floor? And is a support necessary? Remember, we could have cantilever effect here, because when this burner is firing, there's a certain amount of vibration, so we may need supports. Next, we're looking for the fuel and power supplies. Any special electrical requirements, including codes and standards to be followed? And of course, there's the one I have highlighted in red, the site elevation or altitude. Too often, this is overlooked in a burner retrofit, with the burner arriving at the site with an undersized fan and motor assembly, because the field engineer didn't advise the manufacturer that the installation was over 1,000 feet from sea level. Moving now to the performance requirements, we're considering things like the burner's characteristics, including its construction. As I mentioned before, is it of robust construction? And what about the required feature set, including its ability to hold good excess air levels throughout the turndown? And then there's the burner management system, also referred to as the programmer or flame safeguard. Can I use the existing, or is this the time to upgrade? Also, am I burning a fuel oil for main or for standby? How's it atomized? Mechanically? Am I using air? Am I using steam? What is the existing burner's turndown? And do we need more to prevent cycling? How about the fuel air metering? Do we currently have single point, and would the customer benefit by going to parallel positioning? This is a cost-value question, and if the boiler modulates a lot, something to seriously consider. Then what about emission requirements? Is this a non-attainment area where nitrogen oxides, NOx, and CO, carbon monoxide, are limited by local, state, and/or federal law? If so, there are options out there to meet the most stringent requirements. Moving now to the installation considerations, the main thing we have to concern ourselves with, and also impacting the burner selection, is the refractory and sealing requirements. Also, how is the burner going to be mounted to the front head of the boiler? For instance, do we need a special plate for fitting the burner up to the existing burner opening? Or does the front of the boiler have to be modified to accommodate the best burner for this application? And we may need both, a larger plate and also a larger opening in the front wall of the boiler. We'll show you this during one of the stories we'll be relating to you. Or what about the refractory requirement? Do I need to replace the dry oven? What about the furnace liner? What about the throat tile? This is all very important stuff, as the refractory pieces not only seal and insulate, but they aid in combustion performance because the refractory is engineered in conjunction with the burner and the furnace into which it's firing. These are all integral pieces: the burner, the refractory, and the furnace. All right. So much for the refresher on the key points to keep in mind for any burner retrofit, which we covered in detail last May, and as Susan mentioned before, is archived on our website. So now let's move on to what some of you older guys and gals out there might remember: the very famous radio personality Paul Harvey and his daily program entitled The Rest of the Story. Yes, now it's time to relate to you some actual real-life stories involving two very different burner conversion jobs, tell you how they evolved, how they were quantified, how they were engineered, and then installed, including the hurdles that needed to be overcome for a successful installation. We're going to start with a large 1 million square foot hospital facility in Milwaukee, Wisconsin. You know, this is actually, I worked here when I was in high school. I worked in their laundry back in the late 50s. The laundry is no longer there, the room is, but they subcontract their laundry outside now. But the hospital's certainly there, and it's expanded quite a bit over the years since I was there. Going into the boiler room, we find three 1960 Keeler 21,000 pound per hour or 600 horsepower equivalent. These boilers are operating at 100 pounds. However, in the summer, the pressure is reduced to about 80 to save energy. Now, the boilers fire both gas and number 2 oil, and originally came with steam atomization for vaporizing or misting the oil. Now, they also have a Cleaver-Brooks DL76 high-pressure water tube boiler, which they use only in the wintertime, like right now when it's close to below zero out here. And then at that particular time, they take one of the Keelers and they keep it in hot standby just in case. Now, as far as the load is concerned, these boilers provide for heating the building. They also provide for humidification, sterilization, some cafeteria support, and then they provide domestic hot water through a separate heat exchanger. Now, several years ago, some of the facility engineers were concerned about the rising cost of fuel, and they thought it might be a good idea to replace these boilers with new, more efficient ones. Well, when confronted with the cost associated with the total replacement, they went to the boiler chief, Rick Brown, and they asked his opinion. Well, Rick is an old boiler guy, and he inspected the existing boilers and found them to be sound for their age and worthy of some investment in order to improve reliability and energy costs. Rick's recommendation was to begin by replacing the burner management and combustion control systems, as the existing systems were basic loop controllers and they were seriously outdated, and securing parts was becoming a real problem, certainly affecting reliability, one of the main drivers. Well, approval was received for retrofitting all 3 of the keelers with the new burner management system and combustion control system. But unfortunately, Rick was fairly new to the job and was not made aware of other problems which had been occurring with the boilers on a periodic basis in the past. And that was some pretty rough lights had taken place on several occasions. And it wasn't long, quite frankly, before Rick experienced some himself. And rough light was kind of putting it mildly. As you can see in the slide now, the combustion was going extremely rich. And it became apparent to Rick the burner wasn't atomizing the oil properly anytime they switched to and burned the alternate fuel number 2 oil. Now, to remedy this, a major overhaul of the system had to be made, as it wasn't just poor atomizing taking place. The nozzle wasn't being purged properly before a relight after shutdown. So oil was pooling in the furnace. And one day, not only was it a rough light, but it was an actual furnace side explosion. What you see on the screen in the lower left corner is the aftermath of a fireside explosion in a large water tube boiler. And though this is not the Keeler boiler we're referring to, it does give you an idea of what it looks like. Now, on the right of your screen, you see an arrow pointing to the casing, which had to be replaced because it had gone round from the explosion. You also see the furnace wall tubes, which were to be touching or tangent, forming the seal, but they were separated due to the force of the occurrence. Well, that was the straw that broke the camel's back. And Rick Brown called their control and service provider, PBBS Equipment, to come in and verify his conclusions regarding the steam atomization being the culprit for the furnace occurrences, and to provide some solutions, including new burner retrofits. Well, PBBS sent its engineers, who later concurred with his assessment, which led to the 3 main drivers on the screen to be the catalyst for change and a request for quotation: safety and reliability, parts availability, and fuel efficiency. Well, the request for quotation was prepared after focusing on the points that you see here, and with special emphasis on the points highlighted in red. How well was the existing burner tracking the load during the day, and was it cycling too often? What were the furnace dimensions so the volume could be determined, as well as the flame limitations to avoid possible impingement on the furnace walls? And what about the draft? This can greatly impact good combustion, and burners vary in their tolerance to draft. And of course, then you need to know the boiler room clearances to be able to install a new burner, in addition to determining how you get the equipment in the room. And then lastly, what are the install requirements? How do we complete the job with the least amount of disruption for this hospital? Time is critical here. Well, following this decision-making, a formal proposal was prepared by PBBS and reviewed with the operations personnel, who then sent it to the executive team for final approval and then go-ahead. And the go-ahead, it resulted in the decision to proceed with the 2 Keeler boilers, with 2 of the 3, and leave the 3rd for later based on fund availability or funding availability. Now, the 2 boilers then included what you see on the screen: front wall modifications. They were going to install 2 high-efficiency burners. They were to be air atomizing and not steam. They were going to increase the turn down to 10-to-1, and at the same time upgrade the existing BMS, the burner management system, and the combustion control system, Then they also had to integrate with the existing building management system for monitoring. Now, collaboration is key in these jobs, not only in the proposal stage, but also in the development of the final engineering details and then the execution of the job. Now, in this case, it involved close dealings with the CB representative, as I mentioned, PBBS Equipment, and their engineering department, who got extensively involved with the location decisions, including assessing and conveying of the equipment into the boiler room, the boiler front wall modifications they had to engineer, the actual burner install, and then the final wiring details and hookups. And then Cleaver-Brooks product engineering got extensively involved with the burner selection based on the feature set that was required and the furnace limitations. Now, they also engineered and provided the new burner mounting plate along with the required refractory dry oven and then the throat materials. Now, through the process, and this is key, the customer remained totally engaged and was very helpful in assisting to assure the project moved along and stayed on track to meet the anticipated deadline for completion, which was not to exceed 2 weeks. Now, one of the assigned customers' contributions was to inspect the stack dampers coming off of each of the boilers to be retrofitted to assure integrity and free movement. Now, it's good they did, as they found one of the dampers to be defective and not properly closing, which allowed a constant stream of air to be pulled through this boiler when it was offline because of the high stack draft, and it cost needless energy dollars as a result. Now, as you can see, this was fixed by welding strips on either end of the damper blade. Now, as mentioned previously, our representative, PBBS Equipment, was responsible for engineering and rebuilding the front wall to accommodate the new burner, and they were given all the dimensions from Cleaver-Brooks as far as the burner is concerned and what it would require. Now, this entailed removing the old burner and then demoing the wall and then rebuilding it, as you see here in this picture, which also includes a larger burner opening than they had previously. And once the wall was rebuilt, and with the drawings for the new dry oven and the throat in hand, the PBBS sales engineer, Scott Hosley, checked all the dimensions and then gives the thumbs up, signaling that everything will fit. Now, simultaneous with these activities, Cleaver-Brooks and PBBS Equipment were busy designing the electrical circuitry not just for interfacing to the new upgraded burner management system, but also to the combustion control system, which included parallel positioning with 10-to-1 turndown, automatic draft control, modulating feed water control, and a variable frequency drive on the combustion air fan motor. Then additionally, PBBS engineered a tie into the building automation system, which provided the monitoring capability that was desired by the customer. Well, from here, the front wall casing was modified and reinforced to accommodate the new burner. And once the burner and controls arrived, the materials were conveyed into the building through one of these large overhead doors that you see on the left here, and then through a series of hallways which led to the boiler room, also earmarked. This, of course, had to be well planned before the equipment arrived and was offloaded from the delivery truck. The burner now in the boiler room, the refractory dry oven and throat are installed, and the burner is mounted to the reinforced casing, which matches the new burner plate. And what they did is they used a frame and hoist, similar to what's shown on the screen now, to get that burner in position for bolting to the new front wall. Well, once everything was connected, the system is wrung out electrically. And now with the new burners online, it's time for readings to be taken. so that we can prove that what was promised is actually taking place. And based on the customer's reaction, this is Rick Brown, by the way, the 8-day install, remember they said no more than 2 weeks, it not only beat the time requirements set during the planning stages, but delivered everything else as well, including a much better and more efficient fire in the furnace and with no rough lights. The next job I thought would be of interest to you today is St. Paul's Towers in Oakland, California. Now, this is a 213-room, multi-story facility for seniors requiring heating and domestic hot water 24/7. When the building was initially built, it included these 2 hot water boilers of the flexible water tube type and having a natural gas input of 6 million BTUs per hour each. That's about 150 horsepower each. Now, the picture on the screen in the upper left corner shows you how these boilers are basically constructed with flexible serpentine tubes which are held into place by upper and lower headers, and of course includes multiple passes. In this particular case, it's 5 passes. So as mentioned, these boilers are providing the heat for the building and the heating medium for a separate water-to-water heat exchanger for supplying water for sinks and tubs and showers. So you might ask the question, well, why the retrofit? The burners certainly look like they're in excellent working order. What drove the change? Well, it wasn't the burners' condition, as noted. It was the inability of these burners to meet the newly enforced California regulations requiring NOx levels of 15 parts per million or less. Now, these burners were generating over 100 parts per million because the law did not include limitations on boilers of this size when they were first installed, and they couldn't be grandfathered. So the only choices were to retrofit them with FGR, flue gas recirculation, to try and meet the requirement, or the other thing would be to replace them with burners with low NOx equivalents. So when these options were discussed with the Cleaver-Brooks representative on the job, R.F. McDonald Company, it became obvious very soon that other driving issues were at play here. Firstly, cost was a major issue, not only initially, but operationally as well. And then there was the issue of gas pressure. The gas pressure at the meter was low. It was less than a pound, and it couldn't be raised. And going to a gas booster was certainly cost prohibitive for St. Paul's Towers. This was a key issue, as employing flue gas recirculation would not only elevate the electrical consumption compared to a new burner, but probably, and more importantly, the gas pressure requirement. So this then left a new low NOx burner as the only option. But which one would best meet all the requirements, including the NOx performance, best efficiency, retrofit ease, quality, and acceptable life cycle? Well, to answer these questions, R.F. McDonald's service or sales engineer, Don Patton, sat down with the facility engineers at St. Paul's and quantified these items in order to best propose a suitable retrofit burner. So, of course, we had to define the boiler details, and of course he knew that, being a Cleaver-Brooks representative. Also look at the furnace dimensions and secure those and confirm those. Burner clearance to floor and support required. The gas pressure, verify that, make sure that they only have that limited amount. What about the stack and venting suitability? The power supplies and the control panel location for the when the new burner is installed. What about the system control needs? Is there any inadequacies there? And then the boiler room clearances. How are we going to get access to the mechanical room? And then the install requirements, especially as it relates to timing. Now, the reason I've got the points highlighted in red is because of their extreme importance in properly selecting the proper burner for the job. Remember now, and I can't emphasize this enough, it's not just a matter of having a burner that fits nicely to the front of the boiler and has all the dimensions. No, it's much more than that. the burner has to be compatible with the furnace that it's firing into. It's extremely important to get the total results, to get the maximum results. Which is why the experienced sales engineer deliberatively reviews the furnace dimensions to determine not only the volume, but the length and width in order to negate the possibility of flame impingement on the walls of the furnace, causing combustion rumbling, sooting, and CO formation. Now, in this particular case, Don Patton had ready access to Cleaver-Brooks drawings, so it was easier a task than normal. But being an ex-field technician, he checked it himself anyway, just to make sure. Then there was that all-important dimension of the dimensions of the clearance from the center line of the existing burner opening to the floor, and if the burner needs to be supported based on this dimension as shown here. Very critical dimension. Then, similar to the hospital job that we just reviewed, the sales engineer, Don Patton, went back to Cleaver-Brooks Engineering to discuss his findings and customer needs in order to collaboratively decide on the best option for this particular job, all while involving the customer as necessary to expedite the process and then keep them informed. This is very important. And as you can see on the screen, the answer was to go with a low-NOx fiber burner, which premixes the fuel and air similar to a Coleman lantern and delivers all the customer's needs in a very cost-effective manner. The proposal was then formally drawn up and included the following: the new fiber burner with parallel positioning and a 5-to-1 turn-down ratio. It also called for new doors for burner mounting on the front of those boilers, new control panels, new digital hot water temperature control with return temperature limit. These are non-condensing boilers. So we wanted to have, RF McDonald Company wanted to have a control system put in place to be able to stage these burners based on return water temperature, but also then include a three-valve or a three-way valve to assure that the return water coming into the boiler was above 150 degrees to prevent condensation. And then they also wanted to have automatic setback at night, reduce the temperature because it didn't need to have that much heat in the building at that time. The other important detail before a final PO was issued was to confirm how the new burners were going to get into the boiler room, which was on the roof, which meant they either had to be crane lifted to the roof from the outside, which was very costly, or brought up through an elevator. Well, for cost reasons, it was decided to bring them up through the elevator. But to do this, Cleaver-Brooks had to ship the major components of the burner in separate pieces, as you can see on the screen, and then the pieces had to be reassembled in the mechanical room. Well, CB agreed to do this, and then the PO was issued. Now, once the burners were reassembled into a complete package in the mechanical or boiler room, they were installed in the boilers using a chain hoist, as you can see here. And because the proper planning and coordination had gone into the job at the outset, the supporting platforms were fabricated and placed in position before the burners were bolted on to the newly fabricated burner doors. And the control panels were conveniently mounted in front for easy access. Well, in the final analysis, the job took less than a week to completely install because of excellent planning and execution. And in the end, the customer received all they had asked for: NOx below 15 parts per million, higher burner turn down than had been going on before. They had a 3-to-1 turn down capability before, now it was 5-to-1. They had a superior hot water system control. And best of all, they enjoyed fuel savings of approximately 30% on a $38,000 per month bill. Great stuff. So, that's the rest of the story, as Paul Harvey would say. Now here's some takeaways for you today. Most burners are replaced because they're worn out, average 15 years. But remember, the drivers will dictate the need for a replacement. Make sure that the drivers are revealed and followed. So in other words, the sales engineer has a responsibility to make sure he probes or she probes very, very closely with that customer to find out what are the drivers here. We don't want to do it more than once. And we don't want to install a burner that's not needed. High excess air causes high waste of energy. 2% increase in O2 above that 3% we talked about, 1% energy loss. Some burners are undersized to load. Check with the boiler manufacturer before replacing with a larger capacity burner. You could be overfiring that vessel. Some are oversized, causing expensive, the burner is oversized, causing expensive cycling. Seriously consider replacing in this particular case, but check with the boiler manufacturer, because you might get into condensation issues if you put a smaller capacity burner on a larger boiler. The burner must be matched to the furnace for best results. Parallel positioning is the best combustion control strategy over single point. Before deciding, make sure you review the application, the performance and installation requirements for the job with the customer, and deliberately plan the job from start to finish. How about some questions? You can text those in. We'd appreciate them now.